And he's going to speak about quantum electronic dynamical density functional theory.
Thank you very much. Yeah, good morning. I hope you slept well after yesterday's dinner. And thank you to all of you who managed to wake up and came. Well, it's a great pleasure to speak at this conference. I'm really grateful to the organizers for inviting me, and for me that is especially convenient because I don't need to travel anywhere. Total Energy came right next to my office. And of course, nothing comes for free, and I have a special pleasure and privilege of giving a first morning talk after the conference dinner. Yeah, so the theory I'm going to present is not yet fully ready to the real material science applications. Most of you are probably doing. It's more the demonstration of conceptual possibility to extend the electronic structure density functional theory framework to the new realm where not only the electrons should be treated fully quantum mechanically, but also the electromagnetic degrees of freedom, which are normally described classically as external fields. Here is the outline of my talk. I start with a brief experimental motivation to convince you that it makes sense indeed to do that. I first remind the framework of the standard, what I would call classical TDDFT, just to contrast it to the new formulation. And then I go to the setting up the formal mathematical problem, the pool many-body problem in the context of cavity QED, and eventually I will formulate the extension of the theory to this cavity QED framework. If time will permit, I will discuss the possible implications of this formulation for the theory of open or dissipative quantum system, and then I will present the summary of main results. So, the experimentally, the story, the beginning of the story can be dated back to 80s when people managed to experimentally create high-quality resonators and to build up strongly bound states of the Rydberg atoms, of the electrons in the Rydberg atoms with the photons of the photon modes of the cavity. In 2000s, the new stage came with the advent of what is now called the circuit QED. And the first demonstration was the artificial atom, macroscopic, mesoscopic artificial atom, so-called Cooper pair box, embedded into the high-quality microwave resonator. In the next decade, there was a series of further developments in the circuit QED where people managed to embed into the microwave resonators a more complicated system, quantum dots, the double quantum dots, fully control the correlation and transport effects in the electronic systems, which are coupled to the quantum electromagnetic fields. And then eventually in the last decade, so the first experimental report was in 2012, it was demonstrated that even the chemistry or the properties of molecules can be modified by the presence of vacuum fluctuations of the vacuum electromagnetic field. In the last decade, there were really many, so there was an explosion of interest in this field, and by now there are already 100 publications, and many of them can be found in these very recent reviews. In quantum optics, normally, what people do, they're describing electronic degrees of freedom in a very oversimplified models, like 2-3 level models. And clearly for the systems like that, it is desirable to treat electrons in the full scale of the electronic structure theory. And for me, that was the main motivation to try to extend the electronic structure frameworks to the situations when non-relativistic electrons and non-relativistic electrons living in molecules, in solids, in quantum dots or whatever, which are strongly coupled or driven not by classical, by the quantum electromagnetic fields. And this is what I would call the QEDFT or QED-TDDFT. So essentially, the TDDFT is a non-trivial framework. The extension of the static theory is quite trivial in these situations. So let me first remind you what is TDDFT in the standard classical formulation. Of course, we are dealing with a quantum many electron system. We have n electrons. Everything is described in terms of the many body wave functions, which is a function of n coordinates of n electrons and of time in the time dependent. And this wave function satisfies the many body Schrödinger equation. So this is our theory of everything in condensed matter physics. What we have as the input in the standard formulation of the theory is the initial state and the external potential which confines and drives the electrons. And then the Schrödinger equation, solution of the Schrödinger equation, defines what I call the direct map. So the external potential and the initial state are mapped to the many body wave function at any time t, and any observable we can calculate with as an expectation value of a proper operator. So the standard statement of the many body problem, we find the many body wave function in any observable, in particular what is most relevant for us, the one particle density as functionals of given external potential and given initial state. What is the TDDFT? The TDDFT is based on the highly non-trivial statement that there is a unique inverse map. If we know the initial state and the electronic density at all the times, we can uniquely reconstruct the many body wave functions at all time t and the external potential which drives the dynamics of the system. This is formulated in terms of the TDDFT mapping theorem, first proved by Runge and Gross in 1984, which can be stated as follows. The many body wave function and the external potential are unique functionals of the initial state and the basic observable, one particle density. This seems to be a simple statement, but there is a highly important practical outcome. The exact density of fully interacting system can be calculated by solving a quantum problem for n fictitious, fully non-interacting particles. This is so-called the Kohn-Sham construction. In practice, what we can do, we can solve the problem of n non-interacting particles living in the presence of the effective potential, which is the external potential, Hartree potential, which we know exactly, and some exchange correlation potential, which we know to be universal functional of the density. And because of this mapping between the potential and the density, we know that the exchange correlation potential can be adapted in such a way that the density of the non-interacting system is exactly equal to the density of the proper physical interacting system. Now, this theorem allows to hide all complications of the many body problem in one compact object, which is the exchange correlation potential. Of course, this is only the beginning of the story, and we need the proper approximations. But as long the approximations are set up, the simplifications, computational simplification is tremendous. So now let us switch to a more complicated system and include the other degrees of freedom, in particular these electromagnetic degrees of freedom in the context of cavity QED. I start with the simple example of classical dipole in a classical cavity. So I have a cavity which supports a number of transverse electromagnetic modes and a dipole, say the electrons attached by spring to an ion, which is sitting inside the cavity. Normally, the cavity is macroscopic and the electronic system is microscopic. And these, normally the wavelength of the electromagnetic fields is orders of magnitude larger than the size of the electronic system, and then we can always treat the electronic system from the point of view of electromagnetic degrees of freedom as a point dipole. So this permits us to use a so-called dipole approximation, which is always, practically always works very well in all contexts of the cavity QED. So now how we describe the dipole. The dipole is, dynamics of the dipole is described by the Newtonian dynamics. So there is a spring constant and the electric field of the cavity modes. Because there is a charge, and the motion of this charge gives an electric current, which is essentially can be written as a time derivative of a local dipole moment of the electronic system. And because we have an electric current, this current can be fitted back into the Maxwell equation describing the electromagnetic degrees of freedom. So all in all, we have the coupled system of equations, the Newtonian dynamics for the electron, and the Maxwell equations for the electromagnetic degrees of freedom, where this transfers electric field. This is the transverse part of the polarization current. And in principle, there could be some classical antenna sitting in the cavity to excite the cavity externally. It can be cable or antenna or whatever, which is this external transverse field. So that's a classical description. And now we want to go to the quantum mechanics. And we know very well how to quantize the dynamics of the electrons and to quantize the dynamics of electromagnetic field. It's not immediately obvious from those equations. Yeah? So to quantize things, we have to first to bring the classical theory to a Hamiltonian form. So we have to reveal the Hamiltonian structure of the Maxwell equations. And this can be done in a surprisingly simple way, just by changing the independent variable describing the electromagnetic field from the electric field to the displacement field. If we just rewrite the Maxwell equation in terms of the B field and D field, then we see that they already have a quite obvious Hamiltonian structure, yeah, this equation and that equation. And indeed, by introducing the proper canonical commutation relations between B and D, we can find that the right-hand side of the Maxwell equation can be written as a commutator or canonical bracket of the electromagnetic Hamiltonian, which is the familiar form of the electromagnetic energy, commutator with B and D. This reformulation shows that the B and D are proper canonical conjugated pair of variables, not B and E, but B and D. And that is very important point to understand. In the cavity context, things can be further simplified because the modes are discrete. So we can solve the Maxwell equation for the electromagnetic field and expand the B and D fields, expand them into the cavity modes. The coefficients of expansion, I rescale them. This is Q and P. These are just the properly rescaled coefficients of expansion in such a way that these canonical commutation relations translates to the usual Heisenberg commutation relation. So Q and P, P is a representative of the magnetic field of the electromagnetic field, and Q is a representative of the displacement vector. And now the electromagnetic Hamiltonian translates to this very simple form. So this one is B squared and this one is D squared. And you see that we have a coupling between the electromagnetic field and the electrons, and this coupling has a form of a shift of the D field by the coordinate of the electrons, which is a polarization. The coupling constant here is not surprisingly, it is proportional and it is determined by the strength of the electric component of the radiation mode in the cavity at the position of the electron. So now we are ready to set up the full many-body problem. Now the electromagnetic degrees of freedom should be included into the arguments of the wave function, which is a function of the coordinates of the electrons and coordinates of the electromagnetic field, which is a set of Q displacement variables for the electromagnetic modes. And we have to solve the full many-body problem with the Hamiltonian, which has the usual form of the electronic Hamiltonian and plus the electromagnetic part. This is a B squared and this is a D squared. The coupling between the electromagnetic degrees of freedom and the electrons is given by this shift of the D variable by the polarization of the electromagnetic field. And we can exclude the external driving field for the photons. This is the this is the external current, the polarization of the antenna expanded into the cavity modes. So all in all, what we have to do is to solve the time-dependent Schrödinger equation for our system, and this system can be cartooned in this simple way. Yeah, so we have a many-body system and a set of harmonic oscillator, like a spring elastic hairs attached to the center of mass of the electrons. Oh, God. So now I discuss the solving the many-body problem in the cavity QED context. The standard direct statement of the problem is to give the external potentials driving the photons and driving the electrons and the initial state and solve the Schrödinger equation to calculate the many-body wave functions in time t and all the observables. The observables of interest for me now is the electronic density, which is analog of the usual density in the usual density functional theory, and the expectation value of the displacement of the electric field, which is a representable observable for the electromagnetic radiation. This is a standard direct map or direct statement of the problem in the cavity QED, many-body cavity QED problem. And now we can formulate the main statement of the mapping theorem for the cavity TDDFT. The main statement is the existence of a unique inverse map. If we know the initial state, the electron density, and the expectation value of the electric displacement, we can uniquely recover the many-body wave functions at all times and the driving fields, the fields which drive the photons and the electrons externally. This is the main statement of the mapping theorem. The wave function and the external fields are unique functional of the initial states and the basic observables, which is the electronic density and the expectation value of the displacement. And based on this mapping statement, we can formulate the analog of the Kohn-Sham construction. Now the Kohn-Sham construction is the set of Kohn-Sham equations for one fictitious non-interacting particles moving in the presence of some one particle effective potential, and the dynamics of the Kohn-Sham particles is coupled to the dynamics of the electromagnetic field, which is essentially the Maxwell equation projected onto the cavity mode. So all in all, what we have in the Kohn-Sham construction, we have a possibility to get the exact density of the many-body system and the exact expectation value of the displacement operator and of the electric field, eventually by solving the coupled Schrödinger non-interacting particles Schrödinger-Maxwell dynamics. The effective field in the Kohn-Sham equations is the Hartree potential, the expectation value, the potential from the expectation value of the electric field of the cavity modes, and the rest is the exchange correlation potential. And now all complications of the many-body theory is hidden in this exchange correlation potential. And of course, it is only, again, only the beginning of the story. we have to provide approximation for this potential. So there is a conceptual way to set up the problem in such a way, to hide all complications of the many-body effects, cavity QED effects into one compact object. And now we have to approximate. And here the problem starts, and they are not solved yet. So I can discuss the possible strategies for the approximation. The first of all, well, it would be good and simple way to approximate it in the spirit of the gradient expansion. If I neglect the exchange correlation potential completely, then I may say that this would be the analog of the kind of adiabatic LDA approximation. This fulfills all proper things like the harmonic potential theorem, and it works perfectly well for the harmonic potential by not exciting the photons if the motion is harmonic, because the electromagnetic field is a set of harmonic oscillators, and if electrons are also sitting in the harmonic potential, then the exact solution of the many-body problem is known. This is a rigid motion. And without exchange correlation potential, this rigid motion is properly preserved. So which means that all non-trivial exchange correlation effects should come from the gradients of the velocity, and then it would be desirable to design a potential in the spirit of Vignali-Kohn approximation, for example. This is not done yet. Yeah, the thoughts are in progress. Yeah, I wouldn't say that the work is in progress. Yeah, so the thoughts are in progress. And of course, there is the more conceptually simple strategy to connect, to density functionalize the many-body perturbation theory in the spirit of the OEP approximations. So by connecting the many-body theory with the electron-photon coupling via the to the exchange correlation potential via generalization of the Schramm-Schluter equation. Like in the lowest order perturbation theory, we identify the change of the density due to the lowest order self-energy diagram with the electron-photon interaction with the exchange change of the density due to exchange correlation potential. Yeah, so this is what we call usually the OEP approximation. This is what we have done, and this approximation gives us the orbital functional, and there is a very simple physical meaning of this orbital functional. For the ground state especially, we write the expression for the lamp shift in terms of the one-particle orbitals, and then interpret this as an orbital functional, and then calculate the functional derivative with respect to the orbitals, and then give the OEP potential. Yeah, so that's the direct extension of the OEP procedure, which can be done for the ground state, that it can be done on the Keldysh contour for the time-dependent dynamics. This is the first application, and the proof of principle we did back in 2015, applying this OEP concept to the simple, essentially quantum Rabi model. And we see that for the ground state, there is a quite good improvement with regard to the classical treatment of the electromagnetic field. This is a change of the density, so disbalance of the densities in this dimer, and this is a change of the energy. The energy works much, much better. Yeah? So this is a classical description, this is the exact solution, and the red is the OEP. So it works surprisingly good. In principle, there is one good point in this OEP approximation, because it exactly fulfills two limiting cases. One, because it's perturbative in the coupling constant, of course, it gives us right low coupling constant behavior with the right slopes. And in the high coupling constant, essentially the quantum effects become irrelevant because the stronger the coupling, the more and more photons we generate, and the electromagnetic field becomes more and more classical. So in a sense, this OEP construction gives the right slope here and the right asymptotic here. And then it should fit somehow interpolates in between. It interpolates in between better than classical because this slope is better. Yeah, the classical clearly has the right asymptotics here, but the slope is wrong. And because of that, the interpolation is worse. Yeah, so the OEP works in that sense better. Well, the problem is that in practice it is quite complicated, so it is very expensive computationally. And definitely one needs something simpler. So it seems it works for from weak to immoderate coupling, but it's too expensive. Here I just show an example. This is not my calculation, so the implementation of this OEP was done in the Hamburg group, mostly by Johannes Flick. And this is the example of the QED correction to the density distribution in the azulene molecule. So this is the deviation in the density distribution due to the cavity QED effects. So in a sense, this gives us a real space image of the lamp shift. So work is in progress. Conceptually, there is such a possibility, but there is a problem with approximations. Yeah, this is too complicated. So one needs something simple, and I hope that maybe the Vignale-Kohn-like velocity gradient expansion can give us something simpler. So then I very briefly tell you that essentially this formulation can be very useful for the density functional theory for dissipative open quantum system. If we look on this full many-body Hamiltonian, by neglecting or taking out the driving field for the photons and look at it, then we recognize that this is nothing but the famous Caldera-Leggett model for the description of of quantum dissipation in quantum system. So this is the electronic system harmonically coupled to a set of harmonic oscillators. So if these harmonic oscillators have the constant spectral density in some wide band, then this will give us the ohmic friction. Yeah? And that was the motivation behind this Caldera-Leggett model. So essentially what I developed is a density functionalization of the Caldera-Leggett model. So we have this system. Before we trace out the bars of the oscillators, we set up the density functional theory. You write the Kohn-Shem equation in the presence of the effective field. And since this projected Maxwell equation is just a simple, ordinary second-order differential equation, it can be solved exactly. So we can solve it for Q, for the displacement vector, or for the amplitude of the harmonic oscillator in the harmonic Leggett model, and we can trace it out. So we can express everything in terms of only the density. And we end up with the Kohn-Shem system with the effective density functional, which has the Hartree exchange correlation part and the mean field part. And what is nice, that already at the mean field level, if we would calculate this function exactly, we will recover already at the zero level approximation without the exchange correlation potential, we will recover the so-called dissipative nonlinear Schrödinger equation, which was introduced phenomenologically by Albrecht in 1975, just to write down the Schrödinger equation, which in the classical limit would give us the ohmic friction. Here, at that level, we recover this Schrödinger equation with the ohmic friction already at the zero level approximation without any exchange correlation potential. So this will provide the friction of the motion of the center of mass. Yeah? So this potential depends on the first derivative of the center of mass. This is essentially the radiation friction. The radiation friction for this special spectral density of the harmonic oscillator bus with a constant spectral density. It is designed in such a way to give just a usual friction. So if we say have kind of confining potential, we shift it, then the particle will start oscillate, and because of the motion of the center of mass, it will relax to the new position, already at the mean field level. But of course, if the center of mass is not moving, then at the zero level approximation, nothing will happen. Yeah? If we will change the curvature, then we would expect that because of the dissipation, the system should adapt to a new shape. Here, it will not adapt. It will not feel it at all because the center of mass is not motion. And this should be the work for the exchange correlation corrections. It still have to be developed. So Now I'm coming to the summary. So the main good news that it is possible to set up the rigorous TDT framework for the many electron system strongly coupled to the cavity photons. Clearly, there are many open problems. One is a technical, in a sense that the only currently available OEP approximation is too expensive numerically, but there is also a fundamental problem to the whole formulation. And this fundamental problem is that in the present formulation, the theory gives a simple access to the expectation value of the electric field, but not to the intensity, to the E squared. And this is a problem. This is a problem because, for example, if you would like to describe the spontaneous emission of an electron in a spherically symmetric atom, we put an electron in a p state, and then we expect it, because the transitions are dipole allowed, we expect it to relax down. And when it will relax down, because everything is symmetric, the expectation value of the quantum electric field will be 0, but E squared will not be 0. So in a sense, in this formulation, we will not see anything in the electromagnetic degrees of freedom. So the Q is 0, E is 0. Everything should be somehow sitting in the exchange correlation potential. Conceptually, it should be sitting in the exchange correlation potential, but the problem is that there is no variable for that. Yeah, so the electromagnetic degrees of freedom Maxwell equations just have trivial zero solution. Yeah, so in this coupled Schrödinger-Maxwell dynamics, Maxwell part has trivial zero solution. Everything should be done by exchange correlation potential. And this is clearly probably not so easy to design the approximations which would do that. Yeah, it would be better to directly have the electromagnetic degree of freedom electromagnetic variable which would give us E squared. Yeah, the proper fluctuation. Yeah, the E squared average is exactly what kind of give us the quantum nature. Yeah, that's the quantum nature of the electromagnetic field. That the E squared of average is not 0, even if E is 0 itself. So this formulation suggests the natural way to formulate the TDDFT for open quantum systems. There were a number of suggestions to density functionalize the dynamics of open quantum systems. They were based on the same initial setup. We have an electrons, and the bars, the dissipative bars. But then the previous formulation were like this. So we trace as usual. Yeah? We trace out the bars. We set up the many-body problem in the form either the stochastic Schrödinger equation or the master equations and try to density functionalize it. And this leads to a problem in designing the approximations. Here, we do in a sort of opposite way. We have the system and the bus, we density functionalize it, and then set up the approximations, and then trace out the bus already at the DFT framework, which leaves the hope that it will be that the designing of approximations will be kind of more tractable task. So thank you very much for your attention. That's all I wanted to tell you.
Thank you, Ilya.
I have a question about your introduction of D as the fundamental field. At the very beginning, in the slide, there is formula D equal E plus 4 pi P. In my view, this makes sense only if you imagine the cavity is filled up with a macroscopically homogeneous medium. It has no sense microscopically.
No, this is just a switch of variables. I mean, this P is just a local dipole. It's a local dipole. That's nothing more. But generically,
D and E are not local. So you are mixing let's say, a macroscopic quantity like E or D with a microscopic one, which
that's
is P.
just notations, yeah? This is simply notations.
I don't understand those notations, that's the point.
No, it's simply notation, yeah? So my P is the time derivative of the P is the microscopic electric current. Yeah, what I'm doing, I'm simply rewriting the Maxwell equation.
Left, D, in my mind, is a macroscopic field uniform in the cavity, long wavelength, I would see. E is also a macroscopic field homogeneous in the cavity in the long wavelength.
Well, it depends how you view it, yeah. Because there is another view which I like on the D and E.
We'll discuss
yeah,
it next
that's
day
D is actually the actual the D is actually the actual field. Yeah, so there was this activity by Kirschnitz and co-authors who discussed the sign, admissible sign of the dielectric function. Yeah, and they analyzed what is the proper variable which obeys the causality. Yeah, so what is generated by external fields, and I think this is quite in line with that view.
So
that's the D actually the variable.
Yeah. So next day is to discuss that.
Yeah.
Then I have a comment remaining at the macroscopic level. That means the real fields which are present inside the material in the static case and which can be ideally measured are E and B. Then in the low frequency physics, that means phonons in magnetoelectrics, there are reasons for adopting E and H, which is just the opposite of yours, not D and B, but E and H. So in coupling a phonon in a magnetoelectric material to the macroscopic fields in the adiabatic way, omega, very low omega, zone center ideally, is easier and typically done using E and H, exactly the opposite of what you do.
Okay, good. Yeah, so we can. I think that's mostly the semantics. Yeah. So what?
So thank you for your presentation. It was very well constructed. And I have a question about coherence-driven effects. Because usually in cavity QED, you care about effects that are really tight bonded to coherence, just like, for example, superradiance.
Okay.
Or, I don't know, electromagnetically induced transparency. And I don't see how these problems could be handled in this framework.
Well, okay, that's like Hubbard correlations, yeah, how they can be handled in the Conscient framework.
Right.
They
Sure.
can be. So that's, the theorem tells us that they can be. Everything is sitting in the exchange correlation potential.
Yeah, and that's, I mean, is there, have you thought of a way of, in the future, of course, this is an ongoing work, of course, but how to handle these two very common problems?
Well, okay, I would say that at the level of microscopic description, yeah, so that's if you would treat it at the level of Green's functions, yeah, that's adding the self-energies, yeah, then it is relatively, so we have a physical intuition, yeah, what is there, yeah, so we have an emission of photon, absorption of photon, and from that point of view, the density functionalization of this, it carries out the same physics. Yeah, from the point of view of OEP, it's just another way of looking on these many-body effects. So that is one thing. But clearly, I would say from the conceptual point of view, there could be effects which cannot be easily described within the DFT framework or within the TD-DFT framework. We know this very well. Yeah? So if the behavior of particles pretty much similar to the behavior of the free electrons, then DFT works well. In many systems in nature, we know that that's the case. If it's not like we have a Hubbard correlation, then well, we may fail and we lose the intuition. Yeah, so that's the problem. Here, I would say, for me, the intuition is still lacking. Yeah, so one have to develop intuition, looking on different problems, maybe on specific problems which we can treat in the usual way, try to translate it back to that language, and that's I would say the thoughts. Yeah. So in this framework, which allows to treat electronic degrees of freedom to full extent quantum mechanically without doing few level approximations, these are good for electrons. And if we would translate the intuition from the model systems, where we can treat these coherence effects properly into this framework, then maybe there is a hope that we can somehow. That's the problem of approximations in any case. Yeah? And then the point is to develop the intuition for designing approximations. Or maybe extending and adding the new variables to the theory, yeah? Like these fluctuations of the electric field. It's not trivial. But as usual, also in DFT, right? So to treat magnetism, we have to include the spin density. Yeah, using the spin density, in general, we don't need it at the level of the Hohenberg-Kohn theorem. Yeah? Everything is given, yeah, generically. But extending the set of basic variables like current DFT or whatever, yeah. So we extend the set of basic variables, and this gives us more flexibility for designing approximations. And that could be a way of going.
I'm afraid we have to move to the next speaker, otherwise I'm going to completely run out of time. Thank you very much, Ilya.